Sorry, one moment. Amazing. Okie dokie. So, hello, everybody. I am Lauren. I run DevRel at Fhenix. So, we are building basically the confidentiality layer for EVM networks. Super excited to get into this and talk about privacy, the impact of privacy, and ultimately how we see privacy preserving technology to be able to unlock markets that historically have been untouchable to us. So, I will go ahead and get into it. All right. So we understand that most decentralized applications and most applications in the Ethereum ecosystem are architected for transparency, right? This was one of the core pillars of Ethereum to begin with, and it was something that we saw not as a weakness, but as a design choice we made very, very intentionally. Um, the fact that we have transparency has allowed a lot of great things for verification and for trust, but it ultimately defined the user base that we are now confined to. And so, to have the ability to introduce privacy in certain elements of the application flow or the architecture as it stands, it gives a lot of room for the developer of the application to say, what if we did things this way or that way, and add a little bit of choice to the flow. So, okay, so we look at Ethereum as this glass house, right? We have all of the public balances, all the votes, the bids, the preferences, every behavior ever taken on chain is going to be fully visible for forever. And yes, while this is something that we've all always known, I think thinking about it in the actual impact state is a little bit different because, especially now in the time of quantum, we're thinking about the way a lot of systems are harvesting data that they're going to be able to decrypt later. So, Ethereum, for example, having all of these things that are just sitting there out in the open in that public state, maybe some of these things aren't super harmful to us today or in this moment, but we're barreling toward a future where it actually becomes something quite scary. So all of the sensitive data that we're interacting with, we think about DeFi flows, anything that requires sensitive user data. It all exposes exploitation both from a capital standpoint and just like a general privacy standpoint. So, when we call it a glass house, it's like imagine you yourself lived in a glass house. At first it's like, okay, people can see me, and that's okay because I'm not doing anything wrong. But after maybe a day, 2 days, you're like, okay, every single thing that I'm doing is visible, which means the observer in this scenario is able to see your patterns in such a way that over time they'd be able to intercept them or use them against them or use it in a way that ultimately makes you at a disadvantage. So, a lot of the arguments against privacy historically have been if you're not doing anything wrong, why does it matter? But the baseline of that is ultimately if it's going to impact you negatively from the capital or the privacy standpoint, we don't want to put ourselves at risk unnecessarily. So we have seen existing methods for privacy preserving solutions on Ethereum. We have ZK, MPC, and I know Miha did an excellent talk earlier and got into the nitty gritty of a lot of different things here. So we're all very familiar, but lots of different solutions have existed for this, and a lot of really smart cryptographers had to put a lot of things in place here. But I'm going to do a look through of the way some of them interact independently and a little bit together. Okay, so I mentioned earlier that this is primarily a capital problem, right? Like having information visible on chain and the full transparency that we have now is a capital problem. This means that people are actually losing money to the exploitations that are visible. And so in 2023, the number that was published is $500 million just to MEV losses. So we think about that number and it's like, okay, probably the whales are losing money, or probably, the really, really big time traders are being impacted the most here. But actually, that was not found to be the case. So 75% of these losses from less than $20,000. And that means that it's kind of the retail mid-size users that are actually being hit the hardest, which is really, really eye opening. So the grand total of up to 40% of the total auction value has been extracted by MEV. And this we call it the invisible tax of MEV. It's kind of something that in Ethereum we've always just accepted as a core pillar of our architecture, and it's just something that we risk when we're trading in Ethereum. But when we introduce cryptographic primitives that enable selective disclosure, we can say, well, maybe that doesn't have to be the case. Maybe we don't have to accept this kind of risk when we trade. Okay. So why is now the perfect time to start talking about privacy for, I guess, a lot of reasons, but we can look at the overlap of many different things unfolding at the same time. So we have stablecoin adoption, and this ties nicely into the institutional demand. So the institutions are looking for privacy because it's a requirement for them to use Ethereum-based systems or any public blockchain. They, by law, cannot have payroll be public, for example. Imagine like JP Morgan went off and everything's being done on chain, and that means you can see every single employee's salary that has ever occurred. Like, that's something that maybe on the crypto side we have a little bit more tolerance for, but institutions of that scale are absolutely unable to burden that kind of risk. So they're demanding privacy solutions in order to be able to adopt the blockchain, which means they're going to need some sort of pegged stablecoin. This is going to also need to have privacy preserving mechanisms. If the coin itself shows, okay, well, this person sent it to that person at this time and this amount, it's exposing a lot more than we realize based on just, the single number of the balance or the transfer amount. It actually shows over time the entire strategy. It shows the entire mechanisms in which these institutions are working. So privacy in this aspect is not only layered, but just extremely, extremely critical. And then along with that, right, is that these institutions, they're following a lot of these guidelines and the way that they're approaching it comes from the regulations that are in place themselves. So institutions are not exactly sitting here thinking about, okay, well, we'd like this piece to be privacy because it's for the general best interest of the world. No, it's the SEC said that this has to be private for this reason, and so they're going to abide by that, whether it's something that's easy to implement, hard to implement, or just logically makes sense. This is the way that it's going to be done, which actually works quite nicely because it ends up like a recipe for the rest of us building infrastructure. We say, all right, we understand that these things need to be kept private. We can make them private. So a little bit more on like the timing of it all. I think we being Ethereum have always been interested in introducing privacy preserving mechanisms, but for a very, very long time, the technology and the infrastructure was just not there. FHE historically has been known to be very expensive and very heavy. And while we kind of looked at it as the holy grail of cryptography, it was always okay, but how do we implement it in a way that's not going to break the logic of the application? And thankfully, in the past few cycles, the cryptographers at work have made massive, massive improvements in terms of speed and efficiency. We have things like new FHE schemes being rolled out, and we have hardware acceleration that's being explored. And so, both from the cost and the speed perspective, numbers have gone down enough that we can start to see these real world use cases take place. So, I would call it kind of the perfect storm of cryptographic readiness and ecosystem demand for these solutions. So we call it, this window is now open where protocols are starting to think about this from not like a long-term roadmap, not a one day we'll have privacy, but we need to have this today, not only to maintain competitive advantage, but in order to be regulatory compliant. So a lot of different angles here, but when we bundle it all together, we start to see that we're all very much aligned on the same page. Okay. So, taking a look at some of the markets that we see as being novel and unlockable by privacy preserving mechanisms, we start with capital protection. This is a really straightforward one because the reasons that I had mentioned earlier with payroll, right? Like anytime you're doing payout, you want to keep some semblance of privacy. You want to make sure that the strategy itself and, the different methods that which you're working with are not exposed on chain forever because there's a real risk here of being copy traded or being exploited in a way that actually is a detriment to the entire operation of the business. So there's a lot of different angles here with trading and different avenues that can be taken, but for the most part, capital protection is a broad category. The second one is very exciting to me, and we're starting to see this unfold more and more as of lately, but RWAs. So, how can we actually take these tangible things, these real life assets, and bring them on chain and start to like leverage the benefits of using a public blockchain with the addition of privacy preserving tech on top? So, like, we have real estate ownership here, which is always a really exciting one, but something like this would fundamentally require the use of privacy because you don't want all of the information about the purchase of a home or the transfer here to be public information in this aspect because again you can be exploited for it. So real estate is just one, but there's definitely a few angles there that RWAs are starting to take form, and I'll get into that in a little bit. And the last one here is strategic coordination. So voting is one of my favorite use cases of FHE because there's a lot of different ways that you can vote privately. But when you think about, I have this vote and that vote, and they need to be calculated together, that's the magic of FHE. So anything that involves a DAO, anything that involves voting, anything that requires this like multi-party deals, mergers and acquisitions, large trades having to work together to come to some sort of like bottom line coordinates. This is going to require an encryption mechanism that can be operated on in its encrypted state. So we have multiple new markets to dive into here. Okie dokie. So there's the aspect that I had mentioned earlier when we talk about building with privacy from the get-go or adding it to the roadmap. And I think it's a little bit of a new place that we're entering as, confidentiality as being part of the core design becomes more of the conversation. It can either happen in a binary way, now or later. So the benefits of building now is that you have this clean, composable, selective disclosure built architecture ready to go from the first day. And if it's in a scenario where you say, okay, we'll do parts A, B, and C now, but we'll hold off on the rest of it until it's absolutely necessary, or when funding comes in, whatever the reason it may be for waiting to integrate, it ends up costing more than it protects in the interim because retroactively adding technology like this after the fact, it ends up creating a technical debt that takes a lot of time to fix. You end up having to migrate your users to the new logic. The amount of catch-up that it becomes introduced into the tech is just insurmountable. So, I mean, both for the user's benefit and the application developer's benefit, building applications that are fully private by design is really, really critical. Okie dokie. So yeah, I believe Miha covered most of this, but just I'll go through it like quite quickly. We have TEs, which is hardware. The benefits and limitations here are clear. It's lightning fast, but not so secure. Something came out quite recently, a new exploit on TEs, and it was actually very easy for them to do. So, in the case where you have some data that you want to be loosely protected, you'd like it to be fast, this is a solution, but it must, come with the knowledge that these are not bulletproof and you must fully trust the vendor. So TEs, we have MPC, very exciting to be able to split up the computation amongst multiple parties. You let them collaborate, and then each holding a set of the share of the data is able to make sure that the full data is never recreated, and so it's inherently private. These obviously carry the limitation of coordination. And we see this with people, with machines, with technology, anything. Anytime there's multiple things that are required to work together, it becomes automatically just a bit trickier. But MPC is very good for that purpose. We have ZK, which is obviously the most famous of all of the privacy preserving technologies. It is excellent for proving a statement is true or proving a certain set of data exists. If you want to, prove that something happened on chain, ZK is without a doubt a great way to go. But the shortcoming here is that it can't run a computation. So if you have a piece of data that's ZK proof protected, you imagine you want to run some sort of computation on top of it, you're going to have to decrypt that data first, and it's going to become fully visible to the network. So while it was once private, it's not entirely usable in that state. So we introduced FHE as this mechanism to say, okay, well, what happens in the scenario where you both need the data to stay private, but you also need to be able to use it, manipulate it, and interact with it through the course of the application development or the user lifecycle. So that's what that unlocks. It gives this fully encrypted state, fully encrypted shared state that maintains the state over the course of the interaction with the application. So the end-to-end privacy and like the actual data that's encrypted, you can add, subtract, multiply, divide, anything really that you'd like to do with the non-encrypted version of the data, you will be able to do with FHE. And then through pretty granular access control, you come out and you say, okay, I'll allocate access to person A, B, or C, and not these people over here. Or they can have this kind of access, but not that kind of access. So it's a certain amount of granularity that we're seeing unlocked with FHE alone. Okay, so yeah, I got into it a little bit there, but fully homomorphic encryption is quite a big word, and thankfully Mihada went through this as well. But I like to break it down by the Latin roots. So homo means the same, and morph means to change. So the idea is that we're just changing plain text into a ciphertext that's structurally the same, and because it's a one-to-one switch, or I guess a one-to-one shift, we're able to actually run those operations. So this maintenance of the ciphertext in that state means that the data does remain fully hidden, no matter what you do with it, until the moment you decide, okay, this can be either fully visible to the network or just visible to be unsealed by that one individual that was allocated access. Okay, so there are a lot of misconceptions around FHE, quite a lot. So I went through a little bit earlier about, the too complex, too slow. This is not necessarily a misconception. It's kind of like something that was very true in the past, but is becoming over time not as much of a factor. So, the complexity is easily debunked by saying we have a Solidity library and we have an SDK built in TypeScript, and they use the same patterns as WAGMI, right? In Solidity, you have the uint. Imagine you have like a uint 64. You're going to swap that out with an euint 64 and use it in the exact same mechanism. So really, like, a lot of the switch from designing like a fully transparent Solidity application into an encrypted FHE based Solidity application is quite straightforward. So the complexity piece, yes, the FHE math itself is complex, but that's why we offload it to a coprocessor, or it's done off chain. The too slow, we are seeing rapid improvements in speed. We have benchmarks at milliseconds. We have a new FHE scheme rolling out, which has shown significantly faster speeds, and lots of work is being done on that side. So speeds have come down significantly. Production ready. We are currently live on Sepolia, Arbitrum, and Base Sepolia. This one's fun, but the users don't care. And I work closely with a lot of founders, and we hear this often. It's like, but is there a demand for privacy? Like, if people are already using Ethereum-based applications, like the number of people who use Uniswap or Aave on a daily basis, they aren't so worried about privacy. So why should we build for privacy for our users if we know that non-private solutions are being adopted? It's like, yes, okay, the example that we gave earlier, that people are being financially impacted by this, but also that if we look toward a world where privacy is available and ready to be implemented, the natural progression says that more and more applications will adopt privacy up until the point where it's a given, right? It's something that you don't just say, okay, it would be a nice to have, but it's going to be expected in the workflow. So, while people historically used like public sites and we didn't think about it so much in our email, now we do, so that every website you go to is going to be HTTPS. And we use WhatsApp chats that are end-to-end encrypted, right? Like, these are things that we didn't necessarily demand, but now that we have them, it's just a given. Yep, and then the retroactive addition trap. So those are just some of the misconceptions that we see re privacy as a whole. Okay, so a little bit more about what the stack looks like and how can we tangibly offer privacy in this way to developers. It's Kofi as a whole is not just a coprocessor, it's not just one thing, it's just actually an entire suite of developer tooling. So the smart contract in the Solidity library, FHE.sol, is going to be imported just like any other Solidity library. And this is what's going to actually give you access to not only encrypt and work with the data, but FHE.add, there you can run the addition on your encrypted variables, FHE.multiply, exactly like this. So yeah, that contract is what's going to open up a lot of that functionality for us. Then we have the client side, Kofi SDK. We just upgraded this SDK not too long ago. We're very excited about it. It's that all of the encryption is done on the client side, because if you think about it, if you were to hard code the number 5 into your smart contract and encrypt it like that, then everybody would be able to see that you encrypted a number 5. And while it would work, it wouldn't break, it would be visible. So we make sure that all of the encryption is done on the client side. That's passed to the contract. The operations happen. And then the result is going to be sent back to the contract by way of a hash of the ciphertext. So the full ciphertext is very heavy, but it's never fully stored on chain. Additionally, in the stack, we have the mock contracts for testing. So these are a one-to-one drop-in equivalent to how the coprocessor works, so that you can test this and run things on your own with those contracts. And lastly, for decryption, The Fhenix team has developed a custom threshold decryption network, and this basically runs in multi-party computation to make sure that the full decryption key is split up against multiple parties. It's not just one person saying, okay, we have the decryption key, there it goes. This is a way of making sure that from end to end decryption is something that's handled really very securely and in a very fast manner as well. Also adding to this list, we have a number of things retoken. So in the contracts right now, we have an FHE ERC20. So this is kind of the baseline logic. Think ERC20, but with the privacy preserving logic built in. And down the line, we'll be announcing a confidential stablecoin. I hope I'm allowed to talk about that. Okay, so getting more technical here. I went through a little bit of the different components of how we're going to encrypt data, but if we look at it from the Solidity contract side, just like a basic walkthrough of it so we can see how simple it really is. First, we're going to import the logic from the library, and then you have set your counter and the delta as one of these EUINT 64s. So this is just your typical encrypted 64-bit integer. So the function looks pretty similar to how you would write this normal counter function in Solidity, but we notice here we have the in EUINT, and that's how we pass the encrypted data into the contract. So in EUINT 64 is expecting that, and then we'll do FHE.allow. So this is making sure that you're saying, okay, I'm going to set up permissions for this specific contract to be able to see and interact with this data. And this is really very critical because we have to set up the checks and balances to who can access private data, who being the individual, i.e. the wallet address that's signing, or the contract itself that needs to interact with it. And then we see an example of FHE.add. So it's just going to add the counter plus the delta. Really super straightforward. Now we'll look at a little bit more on access control. This is personally my favorite part of the whole Kofi stack. I think, in other cryptographic mechanisms and honestly other privacy solutions, it's very binary. It's okay, this data is private and now the data is public. So everybody can see it or nobody can see it. And that works in a lot of cases. But when we think about more tricky and more specific DeFi use cases, when we think about building for regulations that are sometimes unclear or different compliance use cases, we need to get so clear on really who can see that data and who can interact with it. So you need to allow access to a certain, I don't know, imagine an auditor. We have to be able to do that in a way that doesn't compromise the entirety of the data that we spent so much work encrypting. So some examples of how this works, we see FHE.allow sender, and this is saying that the current transaction sender is going to be able to decrypt. Oh, sorry, cat. And then another example here, like if we call it FHE.allow global, that's going to say, okay, now I have this set of encrypted data and it served its purpose. So anybody that wants to decrypt it can decrypt it. So think about at the end of a voting cycle, you want to be able to reveal all of the published results. So you're going to say, okay, we've done the voting, we've done the calculation for it, we have the result of it. Anybody can decrypt that. That makes sense. A lot more to be said on access control, but I will leave you guys with the documentation. Okay. So a little bit deeper dive into what exactly can be computed on encrypted values. I went through a little bit earlier the arithmetic, right? Normal addition and subtraction, multiplication, division. But more cool than that is you can do full encrypted comparisons. So imagine this is equal to that, less than, greater than. And then because running, imagine like a traditional if-else statement or a for loop would actually break the encrypted logic, we introduced something called FHE.select. Basically, FHE.select just allows you to compute both outcomes, and then it'll pick the branch homomorphically. So this is because if you were to compute just one branch over the other, it would leak in terms of the amount of gas used. So it would ultimately be like a loss of privacy there. So select mitigates that. And then the last one that I had here was randomness. FHE.random is really, really cool to me because a lot of, imagine the gaming use cases would require some sort of random number generation, which is not only hard in computer science as a whole, but especially hard when we're dealing with encrypted numbers. But we have a function for that. So for any like gameplay logic, this is available. Okey-dokey. All right. So I mentioned earlier that we just upgraded the Kofi SDK that we use. So now instead of it being just decrypt for everybody, we have these two different paths that can be taken for decryption. So the first is going to be a view decrypt, and this is going to just show the value in the UI. So like for anybody who's familiar with, traditional programming, you have basically like read writes and write or read access and write access. So we can think of view decrypt as just the read only access. So this is going to be anytime that you just want to like check out your balance, you want to allow somebody else to check out their balance, you want somebody to see the amount of a transfer, you can use something like this view decrypt, but it's not going to allow any specific manipulation of the data. So in that case, we'll use a transaction decrypt. And any time that the contract is going to need to rely on the plain text, so it's going to have to actually do a sort of unwrapping or the actual tallying, then it will have to run the transaction decrypt. And this is when the threshold decryption network is going to fully return that signature with the plain text packaged in, and the contract will send the verified result back to the chain before it uses it. So two different paths. And then I have a little code blip here of exactly what it looks like. So also relatively straightforward. You have just decrypt for view, and then pass the CT hash and the U type, and then the CT hash here with the permit. Okay. So one more time, we'll just look at the whole operation, the life cycle of all how FHE works from start to finish. So first you encrypt it on the client side. It's going to be submit to the chain. Sorry. Submit back to the chain. The computation is going to happen in the contract side, and then you'll either be able to decrypt for that view or for transact, depending on your purpose and your use case. Okie dokie. I went quite quickly. I have a tendency to talk kind of fast here. So if there's any pieces that you guys would like me to go back to or elaborate deeper on, happy to do so.
Yeah, I think Lauren, like we got already one question when you were the cats when you were gone. Maybe it's more about Phenix itself. Maybe you can ask.
Oh yeah, happy
Sure.
to.
Yeah, I just want to double check. I mean, I guess by the end it's clear. Phenix itself, hi. Phenix, this is your library that you're building, or are you also doing like the server side, the computation? What is your product precisely?
Good question. So yeah, we built the Solidity library and the TypeScript library, but we also handle all of the off-chain computation.
Thank you.
I had two questions, but I guess the first with the off-chain computation, like how many nodes are running for the threshold decryption? Like, is it like only run by Phoenix, or do you have like other providers who are also providing some sort of decentralization?
So when we go live with the TDN, mainnet day one will not be using this off the gate. It's something that we're going to roll out over time, and we're thinking that'll be maybe 5 to 6 months after the mainnet day one. It'll be Phoenix and others, so not just us. We're thinking between five other. It'll be a 3 out of 5 threshold.
Okay, cool. And then also I had one other question. Like, are you using a specific scheme, or are you like switching between schemes when you're based on the operations?
So currently we use TFHE. This is the same scheme that Zama uses. We recently published a paper on a scheme called DBFV, which is instead of being, I believe it went from being comparison based to arithmetic based. So certain things will be faster. Think like the multiplication that used to be quite heavy, and then the comparisons will get slightly slower.
Cool.
I'm happy to link the white paper as well. It's quite a good read.
Cool. Thank you.
Are there any other questions? Yeah, I think Dale had a question. Let me turn. Dale.
I have two. Can you go back one slide?
Can you guys still see my screen?
Yeah.
Awesome. This one.
Yes. So could you go to each of those boxes? And I think I understand, but just be clear, where is the CPU processing data and whose CPU is it?
So the CPU, I guess, like in the context that you're referencing, would be our off-chain coprocessor.
Well, like the encrypt one you said is a client-side library. So whatever program is running, quote, client-side, it's not Phoenix, correct?
It is Fhenix. Oh, well, all of the
It is
computation. Mhm.
even the encrypt, step one.
All of the steps.
How would, then perhaps walk me through, how would I send you data that's not already private for you to then encrypt? I would need, I wouldn't, I would never trust Fhenix to do that. I would only send pre-encrypted data to Fhenix.
For the risk of like Fhenix themselves being able to see it.
In my mind, if I'm going to build a solution that's private, then I don't trust you. I don't trust Fhenix. I only trust myself. So I have some customer and I built somehow trust, or maybe it's my own data. And then I want to use your system to do some computation for whatever reason. So I'm never going to give you unencrypted data because I can't trust you. So how would I use step one? How do I give you data that you are going to eventually encrypt and put it on the blockchain and compute it and then again decrypt it? Where's the trust that I should have or I can have, or where's the encryption so that you don't receive clear text data?
So the encryption being done on the client side is happening like somewhat locally for you. The real piece here is decryption, which we cannot see. We cannot decrypt the data. Like it's encrypted on your client side, and that's something that we can't intercept that process. While we do handle the computation, we don't see anything before allocation.
I agree on the compute, the third box. Again, on the first box, whose CPU? You know, there's an Intel CPU, there's an ARM CPU, there's a CPU somewhere that is throwing bits around. Whose CPU is doing that encrypt step?
Yeah, I mean the encryption process itself is being handled by the coprocessor, which lives entirely off chain. So I mean that's being handled also because it's like the ciphertext itself isn't being sent back to the chain. So what we're doing is generating the full ciphertext, the full encrypted result, and then only ever referencing the hash of it from there on out. So yes, I suppose there is. I'm trying to think about exactly where the moment that the clear text would be.
Am I not asking the question clearly?
I'm also not sure. I have a bit of feeling that you misunderstand each other.
Yeah.
To be honest.
I think I understand the question. You're
You're already
asking like
saying it's happening client side, which means it's happening on the CPU of the person that is using the service. So if I were to use it, the encryption would happen on my own machine and not in your cloud.
sorry, it's a bit hard to hear. I don't think you have the microphone.
So I think I'm just paraphrasing your question in a different way. It's not actually my question, but so if I were to use Fhenix, the encryption would happen on my own laptop, and I would send encrypted data to your coprocessor or to the blockchain. Correct?
And you would send it, sorry, the last part cut out.
I would send you the encrypted data. Only encrypted data would leave my computer.
Yeah.
Okay. Does that answer your question?
What I'm trying to get the answer to for, I think what you're like really asking here is at what point would Fhenix be able to intercept the clear text data?
No, not, I can figure that out myself. The first step, what I'm trying to understand is you've built a library of, you know, it's written in C or it's written in Node, or you built some library. And I'm going to run that library on my laptop. Is that correct? As an example, like I could boot up Linux right now, download your library. I could write a little app using your API, your library. And that library that's running on my laptop does step one. It does the encrypt step. Is that correct?
The TypeScript library, correct?
Okay, TypeScript, thank you. And now we have encrypted data. It's on my laptop. You now, in that library, TypeScript, have a way for me to submit that to the blockchain directly, or am I submitting that to your proprietary servers?
you submit it to the Solidity contract. So I can actually walk back to this piece here. So once you've run the encryption in the client side, then we have the example here of what it looks being passed to the contract. So imagine you ran that already. This in EUINT is how you send that encrypted data into the contract. That's how it receives it. So now it's taking that as call data of the value, the encrypted value, and then you're able to actually operate on that encrypted value here.
And that contract is on the blockchain, or is it being run in your proprietary systems?
No, this is a normal Solidity contract being deployed to Ethereum, Arbitrum, or Base.
Okay. And then the next step, which I think is compute, is that also in blockchain? I'm thinking it's not. That's now on your servers.
Correct.
true?
The computation step happens in our off-chain coprocessor.
Okay. And then the last step, decrypt, that is also on, it's a different blockchain. I think you mentioned something, had used a different term for it, but that's also something proprietary. That's not something that is public. Is that true, the decrypt step?
Correct.
Now, when it's decrypted, if that's done on your servers, are you sending me clear text? Since the decrypt was done by your servers, how do I get that data in a way that is not clear text? I'm trying to understand the data flow.
Yeah. So in the decrypt step, it goes through the threshold decryption network. So that means that the multiple parties are going to collaborate together to well, not reconstruct, but they're going to work together with their own individual components of the private key, the decryption key, to make sure that they can decrypt that once the access is, I guess, like proven, or you've like made sure that the person intending to decrypt has that predefined access. So the steps are completed, the decrypt happens, and then it's visible on the contract side. So what we're passing back is not like the full ciphertext still or the plain text. We're always working with the hash of the ciphertext.
Okay, thanks.
Mm-hmm. Did that clear that up with the decrypt step?
It's good enough. I got it. I got enough. Thanks.
Is there any other question of anyone else in the audience? Yeah.
Hi. Yeah, I don't really know much about FHE, but so how much compute does it take to run this computations? Let's say like you have a private token and you want to make a transfer, so you have a change of balance into accounts, which is a trivial thing to do in a normal compute environment that is not FHE. But how much more intense is that in FHE?
In terms of like gas costs?
No, or I mean RAM or CPU cycles, or what kind of computations can I do in FHE? To what scale?
Are you a Solidity developer?
Yeah.
Okay, so any normal flows that you're working with right now can be done with FHE without adding significant overhead. Like, for example, we have a lot of projects, think like a private swap, something super straightforward. The introduction of FHE doesn't add any significant latency. The gas costs are not significant added here. Even like the amount of time that the transaction takes is not significantly higher.
Okay, and computation that would be too intense for on-chain Solidity contracts, but for off-chain computation,
Yes.
like how much more, let's say, in terms of magnitude, can I do before I max out the computational capacity of this off-chain compute?
Magnitude, I wouldn't know per se. I don't want to like BS a number for you, but like what we're seeing is that for most normal use cases, they don't come close. The only time I've seen it touched is with like, imagine like 256-bit integer division, 128-bit integer division gets a little bit tricky. Like the really, really big numbers and the really more complex workflows, you start to see some slowdown.
Okay. All right. Thank you.
Question.
Oh.
You don't see, but it's in the back.
Hi. I had a talk with my friend, Claude, because I don't understand the FHE, that's why I'm kind of wanted to understand a little bit this. And basically, it kind of says that we have a threshold network which uses MPC to kind of decrypt information. And at this point, you're basically all the kind of the nodes are run by Phenix itself. And
They won't be.
please tell me if I'm understanding this correct, because also it's like just AI swap here.
Right now we're in
And
testnet.
that's not possibility to run other nodes. It's not currently not in the plans to run for others to run these nodes. Is this a kind of a theoretical issue there? Like, could you explain maybe a little bit this, and if my understanding is correct?
So currently we're in testnet, so a lot of this doesn't quite apply at the moment. But when we go to mainnet with the threshold decryption network integrated fully, we will have multiple different parties that we choose, right? Like I am not sure how the product team is thinking, like the whom exactly here, but no, it will not be open source so that like this person or that person could just spin up their own node, because that would introduce new risk.
So in that case, you kind of probably would have to have the other node would have to have your hardware. So, and then in that case, kind of it'd be more decentralized, but still, like kind of the hardware would be, I guess, closed sourced. Yeah.
The hardware will be closed source.
Okay, thank you.
Okay, Lauren, I think we reached the end of all questions. Oh, wait, there is one more question from Dale. Let me go back.
This one is somewhat open, so I would just want to kind of get your kind of free-form thoughts on this. Can you speak to anything about these type of solutions and compliance around government auditing, or just that just general area? Like, one of the things I'm concerned about is, well, one, you could go out of business, or these, servers could go down, and then, the solution's dead. But I'm also concerned that if some government in some country somewhere, since this could run anywhere, it's on the internet, says, we want to see XYZ. And then they come to you because it's your servers and you're running all this kind of in-between stuff. And yes, there's some mathematical barriers that are built into these. But I want to hear your thoughts on what is Fhenix thinking around this kind of challenge.
It's a great question, and there's a lot of really interesting work being done on the compliance front right now. So Fhenix can't now or ever be able to just decrypt the data. That's not something that's within the realm of our capability, because we will not be able to find the access to we won't be able to just retroactively grant access to decrypt that data, right? So that is not something that we would be able to do, even with a warrant or a subpoena or whatever legal document they want to throw at us. So that piece is covered. But generally, I think the way we look at it as the privacy landscape as a whole, and I kind of touched on this with the ZK pieces, that the viewing key model, or what a lot of ZK based systems use right now, is very all or nothing. So they're like, oh, okay, you want to view the data, bam, there's everything, take what you will of it. And that means they can see it, they can see all of it. So in an FHE based system, you're able to granularly say, we allocate access to this person for this amount of time, just this one piece of data, and just until, say, Tuesday at 4 o'clock, then we'll rescind it. Okay, so we have this opportunity to say, if somebody comes back, an auditor or whatever, we can bake them into the contract, into the logic in the first place. If there's a certain regulation that says we must have some KYC in place, or there must be AML in place, you can also programmatically add this to the contract before the encryption steps. So in my mind, FHE based solutions are the most compliance friendly. We have the most flexibility around how can we do that. And while the regulatory landscape is shifting a lot, it's changing very rapidly, we need that flexibility to be able to say, if they up and change their minds tomorrow, we need to be able to write contracts that kind of accommodate those changes. And so we're only able to see that done in FHE right now. But I don't have the answers about what exactly they're going to demand out of us, or what is that going to look like to build fully compliant apps. But I do recommend anybody who's interested in this subject look into a company called Predicate. They're working on contract level pre-transaction compliance. So it basically does those AML KYC checks before the transactions run. It's very, very, very cool the way their code works. They're honestly awesome. I love the team. So constantly showing them. But yeah, there's a lot of things that people are working on right now for this.
Thanks for your comments.
Yeah, can you tell us how do you write predicate? Maybe.
Predicate.
Okay, thank you, Lauren. And I think we reached the end of the questions. Then, Lauren, thank you so much for your presentation.
Thank you guys. Appreciate it.